Alrighty, hi everybody. We're Team 9. We're doing the motor controller for the MSU Solar Car team. Today we're going to be discussing basically how to choose your MOSFETs for a three-phase inverter. And my name's Chris Summer. I will be discussing, basically doing a basic overview on the MOSFETs and the way that the three-phase inverter works.
I'm Scott O'Connor. I'll be going over gate capacitance, switching losses, and breakdown voltage.
Hi, my name is Matt Byers, and I'll be covering the on-resistance, heat dissipation, insulation, and heatsink selection.
And I'm JR, and I'm going to talk about the different package types of the MOSFETs and the different techniques that you can mount them onto the heatsink.
So to give a basic overview on a MOSFET, I mean, we all remember 302 with Dr. Wurzbach. And basically a MOSFET is a switching device. That's its main function. Normally you work in the saturation region where your drain to source is a much larger voltage than your and your gate to source minus your threshold voltage. And again, the MOSFET is a voltage controlled current source. So when you apply a current on the gate, you'll actually produce a current going through the drain. And as you increase your gate voltage, your current will then increase. So, and how you implement that into a three-phase inverter is you have to have a minimum of 6 MOSFETs. You are able to put multiple MOSFETs in parallel per phase to get to increase the current coming out, because your currents will add when you use multiple MOSFETs. So you have 3 phases, and then you actually have 2 MOSFETs, one on the high side and one on the low side for each phase. This here, the red lines are actually showing the current path for your, the way the current's going through it. From the battery, is actually the MOSFETs are being controlled with pulse width modulation, and it actually goes through the high side of phase A and then goes down to the low side of phase B, and then it continues on from phase B, then phase C, and then from phase A on the high side to phase B on the high side. You cannot have the high side and low side on the same phase. That'll short out the motor, and that's how failures happen. And for regeneration, the MOSFETs are actually are turned off. They're actually shorted. The diode that's built into them are actually shorted out, because what actually happens is when you have the rotating rotor, it actually induces a voltage in the winding, which when you have a higher voltage on the anode to the cathode, ends up supplying your current going the other way.
So the next, another consideration in choosing MOSFETs is the gate capacitance. So the gate capacitance determines how fast your MOSFETs are going to turn on and how much current you need in your gate drivers. So in an ideal world, you would just apply a voltage to the gate, or a voltage between the gate and the source, and it'd automatically turn on. But because of these resistance and capacitance of the gate, that doesn't happen right away. So to be able to calculate how much current you would need, so the change in the voltage is basically an RC circuit. You would think you would only need the gate to drain or gate to source capacitance, but you'd also need to take into account your gate to drain capacitance due to the Miller effect. To calculate this, you'd obviously need a differential equation that would solve the change in the voltage across your gate to source and your change in your voltage across your gate to drain, which is also dependent on your gate to source voltage. So the equation kind of becomes kind of complex. A good way to estimate this though is to, on your data sheet, a lot of times they'll give you your total gate charge. And so you take your total gate charge and you divide it by the amount of time you want your MOSFET to turn on. So if you have 200 nanocoulombs of gate charge and you want to turn on in 1 microsecond, you just divide that and you get it somewhere around 0.2 amps. To calculate that's it. And if you look at the math, that's kind of like an average current you'd have going in there. And most gate drivers, when you ask for, like when they display their data for how much current you would need, that's their peak current. So a lot of times you want to take that number and double it. So you'd really want 0.4 amps of current to be able to supply the capacitance here. But then again, that's just an estimation, and to do a more complex analysis, you would need to use a couple differential equations. But at least that estimation can get you in the ballpark. Switching losses are also caused by this. So here's a good example of your gate to source voltage. So when you apply, this black line is the voltage you apply. So if you just apply, let's say 10 volts, your gate to source voltage is going to rise, but it's going to kind of stall out there. That stalling is due to the Miller effect. And then eventually, once it gets through that, it'll eventually rise. And as this is the gate current, so as it's proportional to the voltage across your gate, because all you're doing is you're dividing that voltage across the resistor. So while that's taking place, your drain to source voltage is changing. So when you have your MOSFET completely off, you have a large voltage across it. So that voltage can be seen here. But as you as you turn on the MOSFET, the gate, the source voltage rises, and so therefore the voltage across it decreases, and your current going through the MOSFET increases. So the switching losses mainly occur, so all the power, which is the voltage and the current underneath the curve right there, that's all the power from your switching losses. And so that is that right there is given in joules, not watts, joules. And it's because every time you switch, you get that about the similar power loss. So this is a curve showing as your gate resistance increases, the amount of your switching power also increases. Another characteristic you want to keep in mind is your breakdown voltage. So if let's say you have a 200, your breakdown voltage of a MOSFET is 200. So when your MOSFET's turned off, it can withstand 200 volts across it. But if you exceed that, especially if you exceed it repeatedly, your MOSFET can actually fail. And so we've had MOSFETs in the past that have failed. These are from Minnesota Solar Car team. They have you can actually see the MOSFET actually broke down. And a lot of times when MOSFETs fail, they fail short. And so that will just cause a lot of current going through there, which will also increase the temperature. So we've actually had current or temperature rises that have melt copper before, which is at 1,000 degrees. So MOSFET failure and having a properly spec'd breakdown voltage is very critical in choosing your MOSFETs.
Alright, one specification that you also need to keep in mind is the on resistance, and this mainly affects the efficiency of your motor controller. On resistance is directly correlated to the temperature that you're operating at, as seen by this graph, and this is actually from the data sheet of the MOSFETs that we selected for ours. And as the temperature increases, the on resistance basically almost triples for our application. So keeping the temperature down is an important part of keeping your efficiency high. And over there on the other side is another graph that shows how the voltage and drain to source current affect the resistance. And we did a few simulations on different MOSFETs using MATLAB to predict the efficiency that we would get with each one. And this basically shows the amount of power our motor controller is using, and this is the amount of power dissipated in the MOSFET due to the on resistance. And as you can see, it's a quadratic curve because it varies with the current squared. And this basically graphs out the efficiency with power. And right around between 1 kilowatt and 2 kilowatts is where we'd normally be operating the car at. And around that range, we get close to 99% efficiency with these losses, so that's pretty good for our application. And as I said before, the on resistance varies with temperature, so it's really important to keep the system cool. And this is another graph that shows how power losses increase with temperature. And that graphic over there shows how we'd be mounting the MOSFETs onto our heatsink. And basically, we're just screwing them directly on with an insulating pad in between the MOSFETs and the heatsink. And the insulating pad is very important because we don't want to short the drains of the different phases of the MOSFETs together. So basically, we needed a solution that would be electrically insulating and thermally conductive at the same time. And thermal properties that we took into consideration when choosing our heatsink are the junction to case thermal resistance, the junction to air, and the case to heatsink thermal resistance. And basically, doing a few basic calculations, you can get estimation of what your heatsink should have a rating for thermal resistance. And basically, we just took how much power is going to be dissipated in that particular MOSFET, and then divided it into the temperature differential between the ambient and our max operating temperature. And that ended up being 1.93 degrees Celsius per watt. And this is just something that you could use to get an idea of where your heatsink should be at for operating.
So there are different types of packages that MOSFETs come in, and these are three common package types for the MOSFETs. We're probably going to use the TO247 because of the PCB, and we solder each of these MOSFETs like this, and it's easy for troubleshooting later. It's easy for debugging purposes because we can just take out the PCB and put in a new one, and it will add modularity to our motor controller and we operate it easier. And the second one is the SOT227, which you guys have, and those are mainly used in power electronics because of its good thermal capability, its good power capability, and the internal thermal change within the heatsink, insulation with the heatsink. And the last one is the D2 pack, which is used for lower powered surface mount, and it is soldered directly onto the PCB because of its short leads. It's bent that way so that it's directly onto the PCB. It's missing the through hole and the metal thing, so it's not directly, you can't screw it into the actual heatsink. And it changes the different types of mounts that you can use. So these are 4 different ways that you can mount your MOSFETs depending on what type of package you have. And the first one is the clipping. There's 4 different types of clips that are shown here, and the clips are used depending on what type of heatsink you have, and they apply force on the MOSFET and keep it sturdy and safe from moving, depending on what you're using it for. And this is what we're using. We're just using the through hole on the MOSFETs and directly screwing it onto the heatsink with the insulation pad in between. And the ones that you guys have the screw hole also, and screws directly onto the heatsink with a bus bar screwed on top. This makes it harder to deassemble because of all the screws that you have to use. And the last one is the D2 pack that have individual heat sinks for each one depending on what type of D2 pack you have. There's different sizes, different shapes, and depending on the PCB layout that you have, you might have a top mount or a board layout.
So to sum up, we did a side-by-side comparison when we were shopping around for what MOSFETs to choose for our particular application. The one here on the left-hand side is the MOSFET that we handed out. That's actually in a store-bought, the NGM motor controller that the solar car team was using. And as you can see, one significant difference is the breakdown voltage is only 200 volts when we're actually running at a 100 volt supply. And with the, you can get high voltage spikes from the inductors in the motor. So we really overspec'd that and made sure that, you know, we got 710 volts for that, just for extra protection. And again, the on resistance, fairly similar. I mean, our on resistance is slightly higher, but our actual current is lower. So that's why we actually decided to put 4 in parallel versus the other application uses 2 of them in parallel. So actually our total output current is significantly higher. The values here are at room temperature, and as you actually increase temperature, your current will go down. So this is just from what we gathered from the data sheet. And again, the thermal resistance, as JR mentioned earlier, is a little bit better, but ours is still within the same ballpark. And then the last thing is really just the parasitic capacitances that are in there. Our MOSFET is actually significantly less, so we should have less switching losses and actually faster turn-on time. So, thank you. Questions?
This previous slide, how did you get those capacitors?
The data sheets give you the, basically, they give you the gate to source charges at a specific gate voltage. And when you just divide the charge by voltage is how you get the capacitances. So, and because we're putting them in parallel, you just divide by the number of the MOSFETs we're putting in parallel is how we get those.
Any other question?
How powerful is this motor relative to a typical car, for instance?
It's about 7 watt or 7 horsepower. So it's significantly less powerful than your regular car, but you're also building a car that's made for efficiency. So you really don't want a huge motor. You want to be able to run on as little power as possible. So the efficiency is more the key here versus the amount of power given.
Anybody else? Thank you very much.